So now we want to solve windowing queries for arbitrary non-intersecting segments. Before we see a solution for this, let's first explore what we can do with what we have so far and see why that actually does not solve the problem. But once more, what is our problem? We've given now n arbitrary non-crossing line segments, as you see here, and we want to pre-process them such that given a query, axis-aligned query rectangle, we can report all segments intersecting that rectangle. So this one here, but also the one that's inside, this one, and that one. Again, we have two cases. If an endpoint lies inside, then we could simply use a range tree. But we have to now handle those where both endpoints lie outside. For instance, this one here. So how could we do this? If you want to reduce it to the version with axis-aligned segments, one idea could be to, instead of storing the segments, to store the bounding boxes of the segments. This would look like this here. So bounding boxes are axis-aligned. I could throw them into my data structure that I constructed for axis-aligned segments, so an interval tree with a priority search tree as associated data structure. This will not work. So why will this not work? What is the main problem with this approach? A, we might have segments that actually do not intersect the query rectangle, but their bounding box does. So that means we will not get an output sensitive query time. Or we might have segments that actually don't have a bounding box, or there are too many bounding boxes. This one hopefully was not too difficult. The problem here is that we could have bounding boxes that intersect my query, like this one here, but the segment does not intersect my query. That means in my query I will find that segment, and then I still need to check whether that's actually intersecting. But in this way, and this kind of demonstrates kind of a worst case setting, I might need to check a linear number of segments in this way, which all don't intersect. So that moves my log squared n plus k to actually log squared n plus n, so linear query time, even if nothing is intersecting. And okay, a vertical segment has a degenerate bounding box, but that wouldn't be the problem. And the number of bounding boxes is also not an issue here. Good. So what is our current problem of interest? I mean, we want to solve the windowing query problem, but the problem that we're really interested in is finding these segments that intersect the boundary. I can reduce this to the following query problem. I have an arbitrary line segments, non-crossing line segments, and now I'm querying with a vertical segment. I want to report all segments intersecting that vertical segment. This is essentially the reduction that we previously have seen for axis-aligned segments, just that it's now for arbitrary segments. So let's see whether we could use a solution for that we had for axis-aligned segments. So can we use interval trees? So for interval trees, what we relied on is that the segments that intersect the boundary actually have an endpoint in here. And in that way, we could build a 2D range tree or priority search tree on the endpoints and find the ones that have the endpoint in that region. Here we have the problem that despite, so here's an example, despite having an endpoint in that region, a segment that I would store at this node, so here I'm storing everything intersecting this vertical line. So despite having an endpoint in here, I do not necessarily intersect this boundary. So that's why interval trees won't work here. We will next see an alternative to interval trees, segment trees. In 1D, they will solve the same problem as interval trees, even less efficiently. But we can use them then afterwards as a main structure for the windowing queries to actually solve this problem. We're going to get to know segment trees. And segment trees are an example of the locus approach, which kind of abstractly speaking means we're taking a solution space and dividing it into regions such that in every region the solution is the same. And this is kind of the locus approach for the following problem, namely interval querying. That is, we have now this 1D setting of a set of intervals, and we're going to have a query point. Here's my query point, and I want to report all intervals that contain that query point. We've seen interval trees to solve this problem, but now we're going to see an alternative approach, and that is segment trees. And the idea is this locus approach of essentially dividing the solution space into regions such that within each region the answer is the same. So what does that mean? It means, for instance, that as long as I'm between, let's say, this point here and that point there, so no matter where my query lies in this interval here, the answer in terms of which intervals are intersected, namely this one here, will always be the same. And that's the locus approach. So here we see that we're subdividing the solution space, which is here just the one-dimensional space. My query will be somewhere in this one-dimensional space. I'm subdividing this one-dimensional space into regions such that within each region the answer is the same. And that means I get this region to the left from minus infinity to the first point. We will do this not including the first point, and then we'll have a special region just for that first point, and then between the first 2 points, and so on. And these intervals will be called elementary intervals. So now I've split my space into these regions such that within each region we know what the answer is. And this can be now very easily be turned into a data structure by building a binary search tree on top of this. So how does this look like? Here we go. We have these regions. So here's my first one, just up to the first point, and so on. And then on these regions, I build my binary search tree. Now I can do the following. So let's say I now have a point, and I can very simply query to find the region that contains it. So now here between whatever, P4 and P5. If I now store with this leaf here all intervals intersected, so with every leaf, say this one, I'm going to store this interval and that interval, then I can very easily answer my queries. If I get a point and I want to know which segments are intersected, then I can simply, let's say I have a point somewhere here, then I will first search for that point, and then if here I've stored those intervals, I can report them. This is not yet a segment tree, but let's see how far we got so far. And for this, let's think about what is the storage that I need for this and what is the query time. So here are some options. Linear storage, order log n plus k query time, n log n storage and log squared n plus k query time, or n squared storage and order log n plus k query time. So the correct answer is C. Query time is perfect, order log n plus time that we need to report. But in terms of storage, this is somewhat catastrophic. We need quadratic storage. And why do we need quadratic storage? Because in the worst case, I'm storing the same interval at many, many nodes. So you could imagine if half of my intervals are simply very long, and then let's say half are kind of short, then at all of these intermediate nodes, I'm going to store all of those intervals, all of the long intervals, and that will be too expensive. How can we avoid this? We're going to use the following observation. So the leaves here correspond to certain intervals, the elementary intervals. So the intervals that you see down here. But every internal node also corresponds to an interval, namely simply the union of the intervals of the leaves of that node. So for instance, this internal node here, the leaves are pi to pi plus 1, the point pi plus 1, and so on. So this internal node simply corresponds to the union of those. So every internal node has an interval 2. We've seen the locus approach and how applying it naively gives us quadratic storage. And now we're going to see how to improve upon this in terms of storage. And the idea that we had to improve was to make use that internal nodes in this binary tree also have an interval associated with it. And this is already indicated here. So every node V has an interval that is associated with it. For instance, for this node here, I have the interval from P6 to infinity, and that is simply the union of the intervals of its leaves. So at the leaves, we have the elementary intervals, and then if I look at the leaves of the subtree here, take the union of those elementary intervals, I would get P6 to infinity. Or for this node here, I would get P2 to P4, and so on. And now the very simple idea is the following. We want to avoid quadratic storage, and we do so by storing segments as high up as possible. So previously, if you think of how previously a query worked, when I went here, I would report all segments that cover that elementary interval. So what I'm going to do now instead is I'm going to store a segment at the node such that the interval of that node is covered by that segment. So no matter where in that interval I am, I'm going to stab that segment. But I cannot store it further up. That means I cannot store it at the parent because the interval of the parent is not completely covered by the segment. And of course, this can be true. So given a segment, this can be true for many nodes in the tree, and we'll have to see how many that actually is. But let's first have an example. So let's say I'm looking at here Sj. Now Sj completely covers the interval from pi to pi plus 2. And that is the interval corresponding to this node. And that's why I could store it at that node if the interval does not cover also the parent. So the parent here is this node. The interval of that parent, which includes things from that subtree down over here, goes over up to pi minus 2. So Sj does not cover this completely, otherwise it would have to be that long. So I cannot store Sj here, so that's not possible. So I'm going to store it at this node. And now we can define what a segment tree is. Namely, a segment tree is simply a balanced binary search tree on the elementary intervals. And so for every node, I look at the elementary intervals. I look at all segments that cover all of those elementary intervals, and those I'm going to store at that node. So the canonical subset of a node is a subset of segments such that the interval is completely covered, but if I would go to the parent of that node, the interval of that parent is not completely covered by that segment. And again, S1, if I look at S1, it is stored at all of these nodes. And the reason is that here, if I would go to the parent, I mean, this parent includes infinity also, as 1 does not cover everything down to, or minus infinity down to minus infinity. Same here, and here actually then again this one also includes up to infinity. So also that parent will not be covered by that segment. Okay, and that also already answers the following question. Why don't I store any segments on the leftmost and rightmost path? So as you see, I didn't indicate any segments here, and the reason is that here I include minus infinity and infinity. And now with this data structures, queries are actually super simple, because if I want to query, if I query with a point somewhere, I will simply search for that point in the tree, and while I'm doing the search, I'm kind of collecting intervals, I'm collecting segments, and all of those segments are intersected by that point. So for a query point Q, we follow the path to the leaf that corresponds to the elementary interval that contains that point, and we report all segments that we see on the way to there. So when we visit a node, we don't have to do anything complicated anymore. We can just report all of those segments. Here's an example. If I'm searching for that point, this is my path. I pick up all the segments on the way, S1, S3, S5, and as you see, S1, S5, S3, those are also the ones intersected. Second example, I'm searching for this point here. While going down, I pick up all of the segments that are stored at the nodes, and in this case it would be S1, S2, S3, and S4. So what is the query time? The query just goes through log n nodes, so I will spend order log n time to go down that path, and then for each node I report the segments that are stored there. That I can simply do then in constant time per segment reported. So I will get a query time of order log n plus k. Now we did all of this to improve the storage. So how bad can the storage actually get? For that, before answering that question, let's make the following observation. Let's assume this is one level of my tree, of my binary search tree, and each of these nodes stores, so each of these 3 nodes stores a certain segment. Now this actually leads to a contradiction, because if you look at the middle of these nodes, so V2 in this case, and if you look at the parent of V2, so actually it has to be to the left of V1 and to the right of V3. Being to the left of V1 means that this endpoint of the segment is definitely still left of you, and being to the right of V3 means that this right endpoint of the segment is definitely still to the right of you, meaning that segment includes also the parent node completely, meaning that there's no reason to store Si here, because I could have stored it at the parent. And this leads to the following observation. Per level, there are at most 2 nodes storing a given segment. Now back to our question, how bad can the storage get? Linear, order n log n, or order n squared? The correct answer is order n log n. So why is that the case? Because I'm storing every segment per level at most 2 times. I have log n levels, so every segment can be stored at most 2 times log n times. So every segment 2 times log n is still order log n. So every segment is stored at most order log n times. I have n segments, so this adds up to overall storing n lists of length n log n. the main tree as such, the binary search tree, it's a binary search tree, it has linear space. So the overall storage is dominated by these lists, which overall, because every segment might be stored log n times, have total length order n log n. And that's what we get in terms of storage. Okay, so what do we have so far? So far we solved this 1D problem of interval stabbing now with segment trees. And what we've seen is that we needed n log n storage. We could do queries in order log n plus k time. This can be constructed in order n log n time. And the nice thing now is that the queries are very simple, because for any query, I can simply report everything that is in the nodes that are in the search path of that query point. So now we solved this 1D problem again. Actually, we solved it less efficiently than interval trees, because interval trees didn't need this log n factor. We do need this. But the reason we did this is because this now allows us to solve the problem of windowing queries with arbitrary non-intersecting line segments. And that's what we're going to do next. So what's the problem that we're looking at? We have arbitrarily oriented non-crossing line segments. Those are the black segments here. We want to solve a windowing query with an axis-aligned rectangle. And this we can solve by first finding everything that is completely in the rectangle, and then finding everything that intersects the boundary of my query rectangle. And this can be reduced to the following problem. I have this input, I'm querying with a vertical segment. I want to report everything that intersects this vertical segment. And then we can do the same with horizontal segment and be done. And in preparation, what we've seen are segment trees. So the main data structure here will be segment trees, and then we just have to think about what do we use as associated data structure. So that's our setting here. We have our segments, 2D segments. Now we essentially project them into 1D space and build a 1D segment tree. Or stated differently, we build a 1D segment tree on the x coordinates of these segments. And now we need to think about what can we use as associated data structure. So if you think of what we get from this 1D space, in terms of elementary intervals, it kind of looks like this, where the space is split into these vertical slabs. What does it mean that I'm storing a segment at a certain node? So a node now corresponds to a vertical slab. So I have a node, let's say I have this node V, and let's say this is its vertical slab. Then at that node, I store all segments that completely cover that slab and that cannot be stored further up in my tree. So for example, this Sj here, that does not cover this interval completely, so that wouldn't be stored here. That would be stored at some node further down the tree. But here, for instance, let's have a look at the setting here. If you look at this node here, and this node corresponds to this range here, then what I'm storing here are exactly the segments that completely cover this range. So that's S3, S4, S1. They completely go from here to here, and I cannot store them further up. So here I cannot store them here because this includes something that none of these completely cover. Just to illustrate that also here, so S5 for instance does not cover this interval completely, so it's not stored at that node, it will be stored somewhere further down, as you see in this example. What does that mean? It means that if I look at the nodes, at the segments stored at that node, then there is a well-defined Y order on them, because they completely cover that. So they completely cover that vertical slab, and they cut my vertical slab into pieces. So one piece here, here, and so on. And between these segments on that vertical slab, I have a well-defined Y order. This I can now make use of in the following way. If I now have a query segment, and let's say that query segment, I'm going down my segment tree. So for any node that I'm visiting, I get a vertical slab that contains this query segment. So I know my query segment is in this vertical slab. Now I want to find the segments that are intersected. Because I have a well-defined Y order, to find the segments that are intersected, what I can do is now I build on this slab, and on the segments that completely cover the slab, or the canonical ones to be more precise, a binary search tree. And this binary search tree, a binary search tree is also a 1D range tree. Now this binary search tree will allow me to find everything that is intersected by this. And I'm using this simply like I use a 1D range tree. I search for this point, I search for that point, I report everything in between. Okay, so far so good. That solves our problem. Main data structure, segment tree, associated data structures, binary search trees, or stated differently, 1D range trees. Now, if you look at this combination of segment tree and binary search trees, what is the query time that I overall get? Is it order log n plus k, or is it order log squared n plus k? Keep in mind I was asking about the overall query time, and that is log squared n plus k. So within each of these trees, so I have 1D range trees, so within each of these, the query time is order log n plus k. But then in my segment tree, I'm visiting log n nodes, so I'm querying log n of those trees. So this is this log n. So I'm multiplying log n with log n, and then plus the reporting. So to sum up what our data structure is, as data structure for querying line segments, arbitrary line segments, non-crossing with a vertical query segment, we use a segment tree as main data structure, binary search trees, or stated differently, 1D range trees as associated data structures. In the associated data structures, I use a bottom to top order. In the main data structure, I use the X order, and this will give me a query time of log squared n plus k, and the storage remains order n log n. So order n log n is the storage of a segment tree. In a segment tree as such, in a 1D segment tree, I was simply storing with every node a bunch of intervals. Now instead, I'm storing a binary search tree, but a binary search tree also has linear storage, so that will not change my storage, and overall it remains order n log n. To sum up this result, so if I have non-crossing line segments, I can build this data structure order n log n space and log squared n plus k query time. And if I now apply this to windowing queries, then I have to build this for vertical segments, I will have to build this for horizontal segments, I will have to build a range tree to find the segments that are completely within my range, and all of this Each of these data structures only requires order n log n storage. Each of these data structures, or let's say the dominating term here is log squared n plus k, and that is then my overall query time for windowing queries. To sum up the complete lecture about range searching and windowing query searching, here you have a big overview of range searching data structures, then interval stubbing data structures, then data structures that solve parts of windowing queries, and then windowing query data structures. And if you now want to kind of build your own data structure, it's useful to kind of look at, okay, what are my objects, what's the query that I want to achieve, and then you can piece these things together to get your query time, storage requirements, pre-processing. So in particular, what you very often will need to do is combine these data structures. So think about, okay, if I use this as a main data structure, this is an associated data structure, does that solve my problem? And then based on this combination, what do I get in terms of query time, storage, and pre-processing? And that's all for today.